Hello everyone, welcome to this video. In this video, I am going to explain how to use Matlab for block diagram reduction technique. So let us start with the technique of block diagram. As you all know, block diagram is a technique which is used to reduce many blocks into single block so that we can study it easily. For example, this is a block which is reduced. The system will have some input and some output. So when I have this, so I want to represent the same thing in the form of a signal. X of t is a signal which is input signal, whereas y of t is a output signal. Now the relation between input and output, it is a system that is given by h of t. Now how we can relate in time domain is y of t is equal to input x of t convolution of h of t. The symbol there is of convolution. Now what is convolution? If you are not aware, please refer to any course on signals and systems, or you can simply look into convolution. Basically, convolution method gives you output for a given input in the time domain. That's very important. Since convolution is a difficult process and it takes a lot of time to achieve the output, so we go for Laplace transform of signals and systems, which in turn will make our life easy. So we'll see now how it is. If you can see here, the input x of t is written as capital X of s. So h of t is written as capital H of s. So y of t is written as capital Y of s. The difference between small x and capital X is whether it's a parameter of time or parameter of S domain. So if it is a parameter of S function, we write capital letters. So whenever I write capital letters in my mathematical equations, it usually means it's a function of S. So generally when we are writing function of t, sometimes we may miss writing t, like we write x plus y equals 2. That is, x is literally meaning it's a function of time, y is also a function of time, but we forget. But in order to differentiate, if every time instead of writing it's a function of s, if I don't want to write it, then I can simply write it as capital X, capital H, capital Y in this case. Now output y of s is equal to y of s or simply y equals to capital X into capital H. So the function which was convolution, it's now reduced to simply a multiplication. That's what we just saw. Now here, the same that whatever we had seen in the previous, we are now looking at it as RFS, GFS and CFS. That's the only change. Now input is called RFS, system is called GFS, output is called CFS. Now it is not a compulsory to use any given terminologies except that they have to be capital letters. The terminologies that we are going to use now is a generic terminology used by many authors. The meaning here in general is RFS is a reference input. That's why we use R. Whereas CFS is called as controlled output. That's why we use the terminology C. Then GFS is used for forward path gain of the system. In some cases, instead of GFS, sometimes we may also use HFS, which is feedback path gain of the system. So both GFS and HFS are just a notation. That doesn't mean that you should always write G and H. You can also represent it as X of S, Y of S, Z of S, or any. But what is important is that you have to use capital letters and a function of s. If we forget to use function of s, the capital letters indicate it's a function of s. Now let us go into what is transfer function. As you know, the relation between input and output is CFS equal to RFS into GFS, which is given to the right side. Now it can be written as CFS by RFS, that is output by input in Laplace domain. If I write it as CFS by RFS, it is equal to GFS, which is a system. So basically transfer function tells you the relation between input and output, which is a system in between those two input and output. So as you can see, the transfer function is the ratio of the Laplace transform of output variable by Laplace transform of input variable. Here it is CFS by RFS. Then apart from that, you need to know that we are saying that all initial conditions are to be 0. Why this is important is, for example, if you are going for differential equation and converting that into Laplace, when I say dx by dt, if you make Laplace of this, apart from s or s square or s cube based on order of the differential equation, you get some more terms which are dependent on initial conditions. So if I have a differential equation like dx by dt, and if I want to convert Laplace, it is simply s, because the rest of the terminologies which are used becomes straight away 0, as we have assumed that initial conditions are 0. Please keep this in mind. This is very important when you want to migrate from mathematics perspective to controls perspective. So that is the only important thing. Okay. Now we are going to represent the given transfer function in Matlab. The transfer function can be given in two forms. First form, which is the most generic form which we will be using, is algebraic form. In the algebraic form, we have, of course, numerator and denominator in both the cases. In algebraic form, numerator is also algebraic and denominator is also algebraic. If you look at here, x of n is highest power and it keeps on decreasing, and here y of m is highest power and it keeps on decreasing. Now each order has its coefficient, which is governed by its respective order. A to the power n, a to the power 3, a to the power 2, similarly b to the power m, b to the power 3, and so on. The last a of a naught is having the coefficient for x to the power 0. Okay, so instead of writing x to the power 0, which is equal to 1, we are not writing anything, but otherwise a naught is a coefficient for that. Now we will see other form. In the other form, we have a gain, which is a factor which is given by k, and we can write numerator as function of, or we can say multiplication of roots of the numerator. Similarly, we can write denominator as roots of multiplication of denominators. So if you look at this, if I have this algebraic equation which is there in the numerator in the algebraic form, a to the power n, x to the power n plus so and so up to plus a naught, we can write it as s minus root of or root 1 into s minus root 2 into s minus root 3 and so on up to n roots, because there are n roots. Similarly for denominator. Remember here, for pole 0 form, apart from these roots in the numerator and denominator, we also have some uncompensated value which is a constant, which we call system gain or simply a gain. So we have three things: system gain and roots of numerator and roots of denominator in this form. Roots of numerators are called zeros, whereas roots of denominator are called poles. That we'll study in the theory in more detail. If you have any doubts, please put it in comment section. Thank you for your time.